Today we're going to talk about the hemispherical atomic model. This is the basis for all of HemiChem, that at the core of it, the world at the subatomic level is based upon longitudinal rings, which really are simple to understand and able to be presented visually, not just formulas. So today everything is taught abstractly. You have things in different formulas with lots and lots of formulas. In fact, the current physics even goes to being abstract, and they just make the dimensions x1, x2, x3, x4, and even ones with more dimensions than that in order to solve problems. This is all fine, but in reality, we're really trying to figure out two main things. The shells are spherical. That's the radius, the longitude, or inclination, since I count from the poles, and longitude of the word means count from the equator, and the latitude, phi. Now, also though, those longitudinal rings, which I show here in red, have the axis direction, the rho, which is the circle and the longitudinal ring, and then, of course, the angles around that also as latitude, phi. Now, in reality, the secret of HemiChem is that as you get through this, all of these can be described by 4 dimensions, but it's really just 3D in green with the overlay of one of the dimensions, the radial dimension, that happens to be the axis of symmetry. So that 4th dimension is the axis of symmetry in the hashed golden line down the middle of the cylinder. In fact, that makes what's called quantum numbers. So even the simplest person can understand this really as a globe. So let me show you. You see, in a globe, you have perfectly things. On the surface, that's all at the same radius. Okay, as you go down, you basically have from the pole counting inclination, longitude being the other way. Inclination then gets you a ring all the way around at the same angle. But this line from here to here is the axis of symmetry for that system, and that is called Z, and in chemistry, that's called the one hemisphere and the other. So quantum numbers have the last number as +1/2 and -1/2. It's all really very simple if you understand how a globe works. This is very different than what's taught in the textbooks of the last century. Now, we already see this. If you look in your textbook, you'll see these nice drawings of the different subshells. And if you look at them, you can sort of see their rings. Now, I put them all in blue as rings in 2 hemispheres, one with a matching in the other hemisphere. These are called Bose cylinder in the proof of quantum mechanics. So we can get from here all the way to the most advanced quantum mechanics just using those 4 numbers. Now you also notice that I put here, they have this equatorial. And for the atomic model, it's important to understand that there is a special transitional set when sometimes it's not in one hemisphere or the other, it's in the equator. This applies pretty much on the odd counts, because at some point when you're odd, you can't have the balance across the 2 hemispheres. The S is also 2 at the poles, and you can see that in the bottom. Now these all have fancy names and things like that, but basically all of chemistry comes down to this longitudinal model with 4 quantum numbers. Now let's take an example. Obviously the first one is easy. Subshell S is 2 at the poles. Okay, this hashed line of gold brown is the axis of symmetry through the blue nucleus. Now, 2 at the poles is easy to understand. That's why there's only 2, because once it fills, they want to move towards the poles. There's some pull coming them into the poles. However, once you have more than 2, they sort of have to go in sets. So these have 3 electrons in each hemisphere. This is subshell P. they repel each other, so they can't all fall into the axis of symmetry. That red double arrow keeps them apart from each other. But also, you'll see that the one on the left has one up as the starting point, and it has the poly pair at 180 degrees, so it's exactly balanced through the nucleus blue in the middle to the down for the 3 of the set in the opposite hemisphere. As such, you have a mechanical model that is 1, balanced in 2 hemispheres, and 2, each electron has a balance over on the other side, so that everything is balanced in 3D engineering. Now, this gets a little complicated because obviously they're pulled in towards that axis that in the center by the green axial interaction. And you might call that by various names, but basically there's a pull in, but they're repelled from each other, so they sort of bounce off each other. So if you have 3, the 2 repels, the red arrows, sort of aggregate to be directly outward, the black line. So you have a black line out. That's the force of aggregation of all of the radial electrostatic. And then you have towards the axis, every subatomic particle has an axis, and other particles of different types are pulled towards that. So for the nucleus, the electron is pulled towards the nucleus axis. And we see that. And that creates another balance, the balance between off the axis and in the axis, and that becomes the reason for the longitudinal ring. Now, if you take that, there's some evidence that these are not orbits, which is what Bose decided, and has been the description even in today's texts. They keep on going back to call them orbitals and things like that. This is a picture from Ballantyne at Rice University, and basically he did an X-ray diffraction, and those don't look like they're orbiting. They look like they might be in spherical systems. They might be in even hemispherical sets. You can sort of see them, but I don't think those are rotating. Those aren't moving into things. And that's the difference between the HemiChem atomic model and the Bohr orbital model. There is no movement required. It is multiple forces that balance that. Let's give you another bit of balance. So this is another X-ray diffraction. And this one, well, it doesn't look like they're orbiting. It does look like they're bouncing back and forth a little bit. But then again, that's what I already said. They bounce against each other in the 2 hemispheres because the electrons are locked into those longitudinal rings and locked into the 180-degree pair, which is the ring on the other side, offset by 180 degrees, or pi radians. So this becomes a mathematical model where the proof of statistical mechanics, that Bose cylinder, is the basis for all of HemiChem. And it has great power because there is a natural balance. You see, there's an inward pull. Every proton attracts an electron with radial electrostatic force, okay? But there's also this extra 1 over r. So there's an additional force from the nucleus outward. And so this inward versus the outward basically finds a balancing point, which is the Bohr radius. However, it is a mechanical one. It is static. And that's why I call this extra 1 over r extrastatic, radial extrastatic. And that means that it can bounce back and forth, because if it goes closer, the closer one, extra 1 over r, pushes it back out. If it goes further away, that decreases faster, so you've got more radial electrostatic pulling it back. It is a natural sustaining balance there between the red and the yellow. Now, on the slide before, I showed you the natural balance between the red pushing along the axle and the axial force green. As such, you have a physical model, 3D engineering, for why you get quantum numbers, why you get this hemispherical models, and why you get the chemistry of subshells. So as a result, we should always use position and field things. Thank you.